All right, let me show you my board on this CTS Champlain Tower South board on this. Oh boy. So these are just some formulas I'm working on to see if I can tie it into the structure. I cannot. You put a bunch of formulas in here all you want, but the problem is the structure has so many repairs that had been done or were being done and scheduled to be done that I call it repair vectors. All right, what are repair vectors? It's it's how your repair is going to behave while you're working on it, and also after you finish working on your repair. How do you project it to behave? Do you think it's going to be better or equal to what the original designer was, and was the original designer correct? So it should be superior to the original designer. The original designer being 40 years old in his thinking, their thinking, the architect and engineer combination, especially with the offsets. All right, this I have in a triangular array that works. This is balanced pretty much, except for with this zone in here that doesn't meet. So these triangles, this triangle and this triangle is about the same size. This triangle and that one is not the same size. They're the same size to each other. But so the load transfer is what I'm driving at. And yes, we like to just look at it like this and call it a day. But in reality, it's really how the steel, literally how the steel is going to behave, not how you think it should behave based on the span. This is a piece of carbon fiber reinforcement you're looking at as the guide, as my pointer. It's not how I think this should behave, right? Did you guys see that happening? It's flexing like that, it's springing action. All right, it's not how I think it should behave, it's how it behaves, period. Reinforcement at the bottom, at the top, and across the anchor points, which we know as the shear heads, or the critical shear zone, and also your tributary area between your critical shear zone and your shear heads, between your critical shear zones, which is out here, is a tributary area. The reinforcement is different than it is across the head. In this case, it appears not to really be different. The heads seem just to have one or two pieces of rebar going across them, top and bottom. But they're not really, there's no mat that we've been able to discover across any of these heads. Based on the punching shear performance that I saw, the behavior, seeing him just slip over there, just slip right over like a condom. No plate on top of the head. All right, think of that. Pull it, the plate would have to fracture, right? The round plate. But think of the condom idea, it just slips right down. These just slip down. The decks just slip down over top of all that pool decking. So this wasn't acting as a critical shear zone as we would see it. Ironically, the layer of deck that's actually dead loading on this deck actually contributed to strengthening the deck. Even though it wasn't composite tied to the deck below, I can see it behave in a cantilever fashion. Taking if we look at the pool deck collapsed area right by the swimming pool, you'll see that the topping has quite the ability to cantilever, going out, maybe 6 feet or so without fracturing. It's only doing that through its steel rigidity, if you will. It's able to stay rigid in a cantilever. So that gave us a lot of strength, redundancy across the heads. Will they talk about in this report? Nah, it's going to be discounted because it wasn't composite, it wasn't designed there. They're going to count it as dead load. They're not going to count it for what you see it as. The behavior of each of the steel again. So I have a note here. It says no solo steel. See, it says solo. Steel is not operating solo. It's always being interactive with the concrete, etc. As I say, only love is bond strength and tension in concrete. All right, your bond strength. That's the love you need, the bond strength. All right, without the bond strength, you just got a piece of rebar. It's got to bond somewhere. It's got to connect somewhere, and the bond strength is also anchorage. I don't care if it's even a weld. I don't want to give away that part of the video. Asked a long time ago if anybody could guess this one symbol. I mean, this one piece of steel. I'd be totally impressed. No one guessed it. And I gave away another hint to that now. You know, I take a long time to give away my little hints. So I gave another hint to that one from a long time ago if you're following. I'm going to leave that alone. Best wire. Yeah, I like this wire fabric. This is for sharing with somebody. This is something I'm working on. This is how to recapture the forces back down a pier system with a load above it into the beam system. Recapture this load is up here. How to send it out to the sides. My reinforcement is showing that. Just wanted to get you up to speed a bit to show you what I'm doing here. Okay. Single, maybe two. That would be nice, but it's not double. It's not single. Deflection on shear heads. So deflection here puts stress on the shear heads. So deflection in here puts deflection here puts stress on your shear heads, on your column heads. Deflection here. The repairs they had repairs on the roof here that were structural a time ago, and it's really structural repairs on that roof. I mean, it was serious. That helped with, I believe, when it collapsed, when the building shook. You had a different let's call it a composite existing and repair system, a composite system up there on that roof. And when that building shook, I believe they're around that area is where it failed, and we see that with supporting that would be where we see the structure go down to the roof line. That I think that's come home to roost at the roof line. That repair done back in the day on the roof. And I did a small video on it. I don't know where it is. YouTube ghosted it or not. I can't find it. Maybe I'll do another one on it. The garage area had tons of repairs. So that puts us back to what I said about repair vectors. All right, repair vectors. How do they change the behavior of the structure? So if I come in here and I reinforce this one critical shear zone right here, right, and I make it rigid, and I don't do anything because it's got a crack over there, and I don't do anything down here which is opposing connecting one, and even that one, opposing connecting one, because they're all connected together. They're all going to behave together. They all have to behave together. If I just reinforce this one, what kind of zone did I just create and an issue with this one up here? If I just reinforce two of them, I now have a more rigidity here, so the deflection is the behavior will be different. And that's why you just can't go in there and put supports up everywhere when you go to prop a temporary supported deck. You just can't prop it anywhere you want. You'll be creating negative loads where there might have only been positive loads. With that, so supporting, you really got to know how the deck is behaving, how the steel is, how the steel's laid out, and how you project it to behave. And to do that, you just don't theoretically do it and then put the propping on there. You theoretically do it, and as you're putting the propping, you also check the behavior of the deck to see if it's deflecting or not. Is it changing? Are you changing the profile of the deck? Have you just made a new column over here? Every time you prop, you've made a new column support. You're changing the behavior. So if this span was designed to sag here, to engage the steel, and you put propping here where there is none because you say, oh, look, I'll just break it up with another support. No, you just create a negative moment across the top of this that wasn't steeled, wasn't designed for that. It wasn't steeled. Steel was not placed for that when I say steeled. It wasn't designed for you just to put a prop here, and now you're creating this negative load across the top of that column, and the supports now do new drapes. You're creating new drapes. And this is why propping can be very dangerous when you're propping, when you're supporting. Very dangerous. You can change the loads based on the deflection, and you can know if you'll be changing the loads just by deflection. If you got a flat deck, you're awesome. If you got a flat area here, you're just awesome. But if you got sagging, you got low points, aha, You just can't. That low point is where if you put a pole there now, you're going to make the negative load issues and etc. You're going to create problems. This is actually a short video. This is the last. You'll see the board. I'm going to erase the board. I'm going to keep this. I'll draw it somewhere else, but I'm going to keep that. I'm going to keep this one. The BMA. All right. Well, you know that's my little trick, one of my BMA comments. So I'll leave that alone for now. But I just want you to understand that you just can't support anywhere you want to. You just can't load anywhere you want to. So with that in mind, the car comes in. You've got sagging here. You load a car here. You're putting more stress into that sag zone, that sag area. How the steel profiles. As you go out here, you're putting this more in shear. This is more in tension braking, if you can imagine, if it could pull away. But it can't. The steel goes like, you know, it stair steps over. The stair steps over the steel. Two directional. I'll leave it with this one. This one, I'll leave it with this one. This deck, if you think of it as a beam, was designed upside down. The lower steel in this deck is 1/2 inch steel, as I remember right, and 5/8 at the top. They basically made it upside down deck. This is, I've said this numerous times, but, you know, who knows where this video goes. Take care. Love you. Bye.